Okay, we're going to switch gears here a little bit, and now we are going to begin talking about what's called chemical bonding. We've talked a little bit about this, kind of just a few here and there. We've mentioned a few things. Okay, so we talked about how electrons are organized in an atom. We talked about electron configuration. We talked about the valence shell electron configuration. Okay, and when we talked about that, we kind of talked about how the valence electrons are really the important ones because those are the ones that are involved in the when the chemical reaction happens and when a bond is formed. Okay, and we talked a little bit about, I think we talked about when water is attracted to itself. That's what's called an intermolecular attraction. And then we talked about like within water itself, and we're going to learn how to do this here in the next little bit. But water, I think we've seen this before. Water basically looks like this, and these lines right here, those lines represent the chemical bond. So those are bonds between hydrogen and oxygen. And each of those lines represents one electron from hydrogen. So it's like there's a dot here, and it represents an electron from oxygen right here. Okay, so each bond, each line that we draw is made up of two electrons, one from each of those atoms. Okay, so when we talk about a bond, that's what we're talking about. We're talking about that attraction between one atom with another atom, again, within the molecule itself. So it is an intramolecular attraction. Intra means within, so within the molecule itself, between the atoms. Using the valence electrons of those atoms. Now, there are three main types of bonds. So let's go back to a beautifully drawn periodic table here by me. Well, that's not bad, not terrible. Okay, and right over here between boron and aluminum, so above that line is boron. I didn't draw that part very well. And below the line is aluminum, there's a little stair step. And if you use that stair step, so start right between boron and aluminum, and then go down in a stair step. So you go down between aluminum and silicon, and then between silicon and germanium, and then just zigzag your way down. And what that does, what that line does, is it separates the metals from, and down here at the bottom too as well, the metals from the non-metals. So you can see there's way more metals than there are non-metals. Okay, now, and this works other than hydrogen. Okay, hydrogen it's a gas, obviously. It is also a non-metal. So hydrogen's on the metal side, but it is a non-metal. Other than that, this stair-step thing works really, really well. Okay, there is something about some of the ones that are actually touching the stair step are what are called semi-metals. Don't worry too much about those, but just know that there are metals. Most of the elements on the periodic table are metals. There are some non-metals, but not many. And then there are, again, some of the ones that are right on the periodic table, or right on that stair step over here, right in here, are what we call semi-metals. So the reason that is important is because, again, metals and non-metals is the type of bond that forms depends on what the elements are. So the first type of bond we're going to discuss is called an ionic bond. Okay, and an ionic bond occurs between one metal and one or more non-metals. Okay. So, for example, sodium chloride, NaCl, you can see it right here, NaCl, is that the type of bond in sodium chloride, NaCl, is an ionic bond. And how do I know that? Because sodium is right here on the metal side, and chlorine is over here on the non-metal side. Okay, so it's a metal with a non-metal. Okay, rust. Okay, rust, the chemical formula of rust is Fe2O3. Where's Fe on the periodic table? It's right about here. And where's oxygen? It's right over here. It's a metal with a non-metal. Okay, that also is an ionic bond between those. Okay, and it can even be more than one nonmetal. For example, calcium carbonate is the chemical formula of what's called limestone. Okay? Or marble. Marble is also calcium carbonate. Okay? Calcium is right below sodium, so kind of right around in here. Calcium's in the metal section. And carbon and oxygen are both in the nonmetal section. Okay, so that is also a form of ionic bonding because it has one metal and one or more nonmetals. Okay? What if it has a metal and then another metal and a nonmetal? That won't happen. Okay, it'll have one metal and then it will have multiple nonmetals. Okay? Now, in an ionic bond like NaCl, in that case, what happens is an electron, one or more electrons, is transferred from the metal to the nonmetal. Okay, which means that sodium, if you think about sodium, now we're going to use our electron configuration knowledge. Sodium ends in 3s1, and chlorine ends in 3p5. Okay, the reason that bonds happen is to make these elements more stable. Well, how do you make them more stable? You look right here at the periodic table. Okay, those elements right there are called the noble gases. And the reason they're called the noble gases is just like nobility in life. People want to be like the noble people. Well, the elements on the periodic table react in such a way so that they have the same number of electrons as the noble gases. So sodium with its 3s1 electron, basically, it doesn't say, but I say it this way. So sodium says, man, if I could just get rid of this one electron, then I would have the same number of electrons as neon, and neon's a noble gas, that would make me more stable. And chlorine says, which again it doesn't really say, if I could gain one more electron, then I would have the same number of electrons as argon, which is also a noble gas. So sodium says to chlorine, hey, I'll give you my electron. And chlorine says, thank you, I'll take it. Okay, because what happens is sodium by itself is super duper reactive. Okay, and chlorine is also very, very reactive. But when you put the two of them together, they become really, really stable. Because you guys all know what NaCl is. It's the white stuff that you put on your food to make your food taste better. Not sugar, it's salt. Okay, so sodium chloride is super duper stable enough that we can put it into our body. Okay, if you put regular sodium metal into your body, you know what happens? It starts on fire and it would explode in your stomach and you would die. Okay, what happens if you breathe chlorine gas? You die. It's a poison. Okay, but hey, you put the two of them together and they become so stable that, oh, let's put it in I'm going to put it in my water when I'm boiling water. Okay, to help my food cook faster. Or I'm going to put it on my French fries to make my French fries taste better. Okay, two things that are super duper dangerous because they're so reactive by themselves. When you put them together, they're fine. Okay, so why does that happen? Because the electron transfers from sodium to chlorine, and it makes them both have the same number of electrons as a noble gas, and it makes them very, very stable. Again, the noble gases are the most stable elements on the periodic table. Okay, so the metal, the sodium, right, lost an electron. The nonmetal gains that electron or electrons. Okay, these ionically bonded particles, sometimes we just call them ionic compounds, do form a very large lattice structure. Okay, if you look at salt under a microscope, salt does have these see this very, very flat edge right here and a flat edge right here. Salt is very cubic in nature. Okay, whereas sugar, which is not an ionic compound, we'll talk about that in just a minute. Sugar has a whole bunch of jagged edges, does not have these flat square edges like salt does. Okay, so it's really not just one sodium and one chlorine. It's really a sodium surrounded by a whole bunch of chlorines. And it's a chlorine surrounded by a whole bunch of sodiums. And that makes those bonds really, really strong. Okay, so ionic bonds between metals and nonmetals. It involves the transfer of electrons, and they form these large lattice structures. Okay, they don't conduct electricity in the solid form. So if you take salt and try to run electricity through salt, it doesn't. Okay, but if you melt salt, which you can do, which seems weird. Wait, you can melt salt? Yes, you can turn sodium chloride into a liquid. Okay, they do conduct electricity. So they don't conduct electricity in the solid form, but they do in the molten form, the melted form. And if you put salt in water, water does not conduct electricity by itself. That's a very common misunderstanding. It's the other stuff that's in water that allows electricity to flow. Okay, so pure distilled water does not conduct electricity, but salt water does. Okay, and they also have, because of these lattice structures and the strong attractions, ionic bonds do have very high boiling points compared to the next one we're going to talk about. Okay, so here's some of the ones that we just discussed. Metal, non-metal, metal, non-metal, metal, non-metals. Okay, the second type of bonding that we're going to discuss is what's called covalent bonding. Okay, and the big difference between ionic and covalent is these bonds occur between non-metals only. Okay, so for example, water, remember hydrogen's a non-metal. Hydrogen and oxygen are both non-metals. Okay, that's a covalent compound. Okay, carbon dioxide, carbon and oxygen are both non-metals. Okay, that's a covalent compound. Okay, and even sugar, C12H22O11, it doesn't matter how many of them there are, also forms covalent bonds and therefore are covalent compounds or covalent molecules. Okay, another big difference is, remember with ionic compounds, the metal transfers its electron to the non-metal. Okay, with covalent bonds, they share electrons. Remember that H2O I drew earlier? This is a covalent bond right here, and those electrons in that bond are being shared between the two of them. Okay, sometimes when we talk about covalent compounds, we call them molecular compounds because they are molecules. The term molecule is only used with non-metal compounds. Okay, you'll never hear somebody say a salt molecule. If you do, they're saying it wrong, because salt is not a non-metal compound. Okay, the term molecule is only used when you're referring to compounds that are made up of non-metals. Okay, some more differences is they have, again, ionic bonds have high boiling points, so therefore molecular compounds or covalent compounds have low boiling points, and they do not conduct electricity at all. Okay, and then our last one we're going to discuss are what are called metallic bonds. And a metallic bond is like in your house, the electricity flows through your house through copper wires. Okay, well, how is that copper bonded to itself? It's bonded to itself via metallic bonding. Okay, and this only occurs between just metals of itself. So copper wire, or if you have a gold ring or a necklace or something like that, then those are held together by metallic bonds. Okay, some of the key points to metallic bonding is the electrons are free to move. Okay, sometimes we refer to it as a sea of free or delocalized electrons. Okay, and what happens is, you can see it here, all these little black dots down in here, those are the electrons. And so what happens like a wire is that electricity runs through here. So a whole bunch of electrons basically are on this end, and all of a sudden they start moving through here. Well, what happens to all of these electrons that are here? They start moving this way. And the electrons can move through the wire, and that's what electricity is. It's the movement of electrons that allow the electricity to flow, which turns on your light, which powers your phone, etc. Okay, so these delocalized electrons can move about freely, which again, what causes metals to conduct electricity in the solid state. Remember, that's a big difference. Okay, metals do conduct electricity in the solid state, but ionic and covalent compounds do not. Okay, that's one of the big differences there. Okay, now, because of these electrons that can move around, metals are what we call malleable, and they are ductile. Ductile means you can turn them into wires. We all know that metals can be turned into wires. Malleable means it can be shaped. Many times people refer to their spouses. Say, oh yeah, he's pretty malleable, which means I'm going to shape him how I want him, or I'm going to shape her how I want her. Okay? But metals you can shape in many, many different ways. So some of the different types of metallic bonds you'll see, obviously copper wire, some silver, iron, like iron Iron can be used to make what are called alloys, like steel is an alloy, which is a little bit different from a bond, and then certainly titanium or gold or really any type of metal can form metallic bonding. Okay, so let's look at a couple of examples here. Are the following compounds ionic, molecular, or metallic? Okay, so the first one, I'm just looking at this. Oh, those are all nonmetals. So therefore, and remember, the other term for molecular is covalent. Okay, you can use either one of those interchangeably. So I'm going to say that is molecular, or again, covalent. Fe2O3, metal, nonmetal. So that is ionic. XeF4, nonmetal, nonmetal. So it's molecular. Oh, just a metal all by itself. That's metallic. Magnesium is a metal. Oxygen and hydrogen are nonmetals, so therefore that one is ionic. Nonmetal, nonmetal, nonmetal. Covalent. Oh wait, he said molecular before, and now he's saying covalent. That's right. You can say either one. Hg is mercury. That's a metal. Chlorine's a nonmetal, so that one is ionic. OF4 minus. What does that minus mean in the corner? Nothing. It has nothing to do. Well, it means that there's a -1 charge. It means it's gained an electron. But in terms of what type of compound is it, it doesn't affect it. Those are both nonmetals, so therefore that one is covalent or molecular. Fe, just iron, so that one would be metallic. And calcium carbonate, again, is a metal with nonmetals, so it is ionic. Okay, list 2 characteristics of each type of bonding. So let's just list some things here. So ionic, I'm just going to list a few random things. These are things that you should know. Okay, it has to be between metal and one or more nonmetals. Okay, that's one thing. Another thing might be the electrons transfer electrons between the atoms. Okay, another thing might be the high boiling point. Okay, another one might be conducts electricity. Obviously, this is more than 2. When melted or dissolved in water. If you know those things about ionic compounds, you're in great shape. Okay, covalent. Okay, is just all non-metals. They have to all be non-metals. They share electrons. They have low boiling points. And they don't conduct electricity at all. Okay, and again, sometimes we call them molecular, or we just call them molecules. Those are all great things about covalent compounds. And then metallic, again, just occurs between metals all by themselves. They do have free or delocalized electrons. They do conduct electricity as a solid. Remember, neither of the other ones do. And they are malleable and ductile. Again, way more than 2 for each of them. If you choose 2 of those, really you should know all of this information about all 3 of them. Okay, but that's kind of just a summary of all 3 of them. I guess up here in ionic, one of the other things I would add is they do form lattice structures like that salt particle that we saw. Okay, and that's it for an introduction to bonding there.